Good morning and welcome to the third day of the VGEM 2021. Today we have a very busy agenda, so we will start with the reports from our agency representatives. And the first one to speak is our GEM Program Director from NSF, Lisa Winter. Lisa?
Thanks, Vanya. Thanks for the great introduction. And I'm going to introduce first our Division Director, Candace Major, who's going to say a few words to the GEM community. Candace?
Thank you so much, Lisa. And on behalf of the Division of Atmospheric and Geospace Sciences at NSF, I'd like to welcome everyone to the 30th annual GEM meeting. I'm Candace Major. I'm the Division Director of the Atmospheric and Geospace Sciences Division at NSF since earlier this year. And boy, you all have had a packed week so far. I took a look at your agenda. It's so much exciting stuff going on. And of course, it will continue through the end of this week. It's great to see all the variety of topics that you're covering and also the discussions of community activities, particularly the upcoming decadal survey that will be launched soon. So it's also great to see the strong emphasis on mentoring and student opportunities, and along with discussions of how to build diversity, equity, and inclusion in the geospace field. I'd like to particularly thank the GEM Program Director, Lisa Winter, for the invitation to come to this session today, and also to thank her for her current service as Acting Section Head for Geospace within AGS over the past few months. And in that role, she's really been a valuable part of the AGS and Geo leadership teams. I thought I'd just take a quick moment to highlight a current NSF opportunity that might be of interest to the GEM community. And that's announced in the Dear Colleague letter, NSF 21-102, so that just released earlier this year. And this encourages proposals for planning grants for, I have to make sure I get the program right, Industry University Cooperative Research Centers, or IUCRCs. It's looking for planning grants that address, among other topics, Earth-Sun interactions. So take a look at that Dear Colleague letter if that sounds like it might be of interest to you. And thank you again. And I'll turn it back over to Lisa. And I guess if there are any questions, I'd be happy to answer those either now or by email.
Great, thanks, Candace. And I think we have some question time after my talk. So if you could stick around, that would be great. Okay, perfect. So I'm just going to get my slides up. Thank you, Candace, and to the whole GEM community, thank you and congratulations on 30 years. This year I was asked by the steering committee to give a little bit of a different talk for NSF, focusing more on the history of GEM since this is the 30th year. So I had a lot of fun reaching out to some folks in the community, including the first program officer and one of the first steering committee chairs for GEM, and getting their inputs and their thoughts to share with you all today. So I wanted to start off by using this really poetic description of GEM that Paul Dusenberry, the first program officer, and George Sisko, one of the first steering committee chairs, had written back in 1992. The geospace environment encompasses the highest and largest of the four physical geospheres: lithosphere, hydrosphere, atmosphere, and magnetosphere. Despite its size, its far-reaching structures interconnect and move together in a choreography of organized dynamics, whose complexity is reflected in the intricate movements of the northern lights. The vastness and inaccessibility of geospace encompassing the plasma environment of the magnetosphere-ionosphere system, and the invisibility of its structures pose great challenges to scientists who want to study its dynamics by obtaining, in effect, videotapes of its globally organized motions. A key component of their strategy is the ability to see nearly all geospace imaged on top of the atmosphere. The geomagnetic field threads the volume of geospace and transmits action, TV-like, from the magnetospheric stage down its lines of force onto the atmospheric screen. I really liked that description and thought it's a great way to show the time as well as the importance of what you all do in the GEM field. A short history of GEM then is that this really came from a community effort, and there were many workshops that came before the first official GEM workshops. So there's a lot of organization and excitement in the community that led up to GEM, starting with a workshop back at the University of Washington in 1987. And then you can see there were a series of workshops, and these fed into efforts on the policy side with NSF and also through interagency groups, such as in particular the US GCRP, which is a climate-focused interagency group that's still operating right now and very active. So this multi-agency effort then had a global change program in the late 1980s, and this was focused on climate, and the idea was to do something similar for geospace that had been done for the climate. And also CEDAR had been started just a few years prior, and CEDAR was seen as a really great resource for the community, a way to engage with students, and GEM was looking to do something very similar. The goals of GEM, which are still carried out today, are holistic modeling. So this was what was different about GEM, not taking everything piecemeal like previous efforts, but really trying to do interdisciplinary modeling of the geospace environment and do this as a global coupled dynamic system. The idea was to incorporate models and observations. And as we've heard a lot during this meeting, the campaign organization was how this all got started, where there were very focused campaigns, and multiple people with different backgrounds came together to tackle these issues. So the first GEM meeting, then the first official meeting after these planning meetings, was at UCLA, September of 1991. And that year also coincided with the first GEM Awards. Here I'm showing the abstract that came with the selected awards from that first round with GEM, where the goal stated in the abstract was to support basic research into the dynamical and structural properties of geospace, leading to the construction of global geospace model with predictive capability. I know that these goals are still within the community today and a little bit blurred with space weather, but very much at the heart of GEM. You can see these are the first awards that were made, and there was a lot of emphasis on integrating the observations, the ground-based observations, such as with the magnetometers. And to this day, again, for instance, the MAX system, the MAX mag array was just recently re-awarded, so has been operating since the very beginning of GEM. And many of these efforts that you can see in these titles are still underway and very active types of programs right now, such as solar wind magnetosphere ionosphere coupling. These are all very important topics continuing forward. So the GEM program really is a community effort, but also it's very important that there was support from NSF and from the program officers in order to advocate for the community on behalf of the community and the goal of geospace modeling. So I want to just take a minute to thank all of my predecessors who started this effort and kept it going throughout the 30 years along with the community, and really did a fantastic job in supporting all of the great science and all of the educational goals of the community. So in preparation, I also reached out to some of these program officers and got some thoughts from them. I already shared the first program officer, Paul Duesenberry's thoughts in the opening remark, but I reached out to some of the recent program officers, Carrie Black, who's now moved on to astronomy at NSF to manage DKIST and NSO. Just wanted to convey her thank you and congratulations on 30 years. And she's looking very much forward to seeing what happens in the next 30 years from this great community. I got another really wonderful set of feedback from Mike Wiltberger, who recently went back to HAO after serving as our geospace section head for several years. And his thoughts were that the workshop and community have been essential in developing new ideas and new leaders. The global models that we use today, while not fully funded by GEM, are built around the discussions, ideas, and tests conducted throughout the years of GEM. I really wanted to share also that on a personal note, GEM was so important to Mike because he was a student within the GEM community who became a student leader and then later served for many years on the GEM steering committee. And after that, came to NSF to lead the GEM program and then later the geospace section. So I think it's very inspiring for all of the students out there to see that the leaders in the GEM community have started out just in the same spot that you are today. And then I also wanted to share some thoughts from Kyle Baker, who was the GEM program officer for the longest stretch of time. This was some statements that he had made in the first Geospace Environment Modeling Campaigns report. And he said that in 1989, he attended his first GEM workshop, the observational campaign held at the University of Maryland. And the energy and excitement that was being generated by the GEM community was infectious. From that moment, he knew that GEM was the one meeting that he absolutely needed to attend. He also called out just how important students and using the GEM workshops as an educational tool has been. And I really want to commend the GEM community for keeping this up and for finding a creative way to do that during the pandemic. Even during this difficult time, the GEM community has made it a priority, and the student days have continued in this virtual format. And I think that's really a testament to the dedication of the community. So on kind of some final thoughts on GEM, what I've been hearing and from my speaking with others in the past and from attending this meeting is that where GEM is heading is really back to the future. We've heard a lot about returning to that holistic modeling, not looking at piecemeal. And I really appreciated Larry Kepko's summary where he talked about an elephant. And if you study just a piece of the elephant and try to bring it all together, you're not really understanding or necessarily getting a real elephant. So in the same way, geospace modeling, I'm hearing, again, going back to those origins with GEM and looking at this holistically to understand and be able to predict the geospace environment. Again, I'd like to encourage the community as well to look at incorporating models and observations, and NSF has a lot of great ground-based facilities as well as instrument projects to help you do that. And that idea of bringing together multiple people with different backgrounds, I think is really also feeding into the great efforts of the community with the DEI, and the GEM community has recently started a DEI group. So that, in addition with the interdisciplinary nature, I think is really somewhere that we'll see more of in the future. I want to advertise that in line of that back to the future idea. The geospace section was really happy to put out an integrated geospace sciences call. And I think this will really resonate with the GEM community. The due date is at the end of August. And this is really what GEM is, trying to do these deep and transformative models to understand the geospace system, everything from the sun to the mud. So this is exactly what GEM was founded to do, and I hope that we'll hear see a lot of great participation from this community. And I also want to highlight the facilities that the geospace group is supporting. So we have, of course, incoherent scatter radars to help with your research and your modeling. We have DAISY projects. Several are related to the magnetosphere and the ionosphere, as well as our class 2 facilities, including Ampere, CCMC, and now this year, HARP and the extended Owens Valley Solar Array. So really encourage the community to take advantage of these wonderful resources and incorporate them with the great data sources that you're getting also from space, from NASA and from NOAA and from Air Force and other sources. And of course, we also have significant investments by the magnetospheric physics program in the magnetometer networks, continuing on with that legacy from the first GEM, supporting a similar PIs and arrays from the very beginning. And then along with these, okay, wonderful, thanks, Vanya. Along with the kind of different science that can be done with these observations, of course, there are many different investigations, but these are just highlighting some of those plasmaspheric observations, MI coupling, ELF, VLF waves, as well as ULF waves. So I encourage the community to take advantage of these wonderful resources. So just to conclude then, I want to say thank you from all of us at the Division of Atmospheric and Geospace Sciences. We appreciate all that you've been doing, and want to congratulate you on 30 years and wish you luck into the future. So also, if you are interested, we have a job ad out for a geospace data IPA program director. We really think that geospace data can be improved, and we're looking for someone to help lead that initiative from NSF, which will help with the modeling and incorporating models and observations for GEM into the future. So a special thank you to the organizers, Chris and Chelin, and UNH did a fantastic job once again with this virtual format. Really appreciate all your efforts, as well as the steering committee. I know there were a lot of meetings, and you did a fantastic job. And thank you to all the participants who, of course, make GEM so wonderful with sharing all of your great science and all of your great ideas. Thank you.
Thank you, Lisa. This was very exciting to hear about all previous program directors and their view and support for GEM. So I don't see any questions in the Q&A. The participants may also ask questions if they raise their hand. Is anyone having a question for Lisa or Candace? Okay, so we did get one question in the chat Lisa, is the geospace data IPA position a new position? Can you explain about it a little bit more?
Yeah, wonderful. Thanks for that question. So yes, it is a new position. It's just hot off the presses. So last week, the ad went out and it's advertised in the GEM Messenger and on some other community newsletters, and we're going to advertise it more widely. But it is, we want to bring somebody in who can really lead our efforts to come up with new ideas for how the geospace data will be handled by NSF, and to work with our agency partners at NASA and NOAA on coming up with new solutions, as well as within NSF, because there has been a great drive within NSF to really handle data, because this is a problem that every single field has. So there are some opportunities within SF as well that the community can take advantage of. And this IPA position is really designed so that we have somebody who can focus on that and really come up with great new solutions. So please reach out to me if you have any other questions. I'm happy to answer about those.
And there is one more question. Will there be another FDSS opportunity coming up?
Oh, FDSS. At this point, we don't have a solicitation prepared. However, that program has been very successful. And if there's interest from the community and the funds are available, we would like to have that in the future. But as far as the next fiscal year, we don't. Please reach out if you are interested, though. It helps us to gauge the community need for that great program.
Thank you. So I think we can continue all this discussion via Slack, and now we should proceed with our next talk from our NASA liaison, Jessie Woodroffe. Jessie?
Good morning, Vanya. I wasn't certain that I was next on the list, but I'm happy to go.
Yes, please.
Okay. So I'm going to bring up my slides. And please, Vanya, let me know when and or if you see my presentation. Are you seeing my title slide?
Not yet. We see that you have started sharing the screen.
Okay.
Yeah, it's just sharing black.
Interesting. Okay.
So we can also continue with Howard and come back to you after.
Yes, please. Please do.
Okay, so Howard, are you ready to show us the report and thoughts from NOAA?
I'm getting ready. So let me share the screen. And then it should be sharing now, and I'm going to go to full screen. Are you seeing my screen?
No, it's doing the same thing. That's really weird. Let me try sharing something from my end and see if that changes anything. Howard, if you stop sharing for a sec.
Yeah, let me go over and do that. Sorry, I'm not getting there.
It's okay. I can end your share from here.
Okay, I got it.
Okay. Okay, so it's taking my share, okay. Because you guys saw that, right?
Yes,
The title slide? All right.
yes.
Yes.
Let me try
If-
making Howard a co-host.
If you would, yeah, I mean, if you would like to just show my slides, that's okay too.
Try it one more time, and I'm going to download your slides in the meantime.
Okay.
Yeah,
Yeah,
same
it
thing.
seems to
Okay,
have the same
just
problem.
give me a sec to set it up, and we'll run them from here.
There is always something new every day.
Yeah, you're not kidding.
The miracles of modern technology.
Yes.
All right.
Or maybe I can, while we are waiting, show the reminders for this afternoon. So we take some time later on. So this afternoon, we have a concurrent focus group session. And also in the evening, we will have a geospace system asset session and a GEM queer social. Oh, I see the slides coming in. So Howard, please go ahead.
Okay, well, thank you very much, Vanya. And you asked us to introduce ourselves, so I will say that I'm Howard Singer, and I'm Chief Scientist at NOAA Space Weather Prediction Center. And I'm proud to say that I've been to all but I think one GEM meeting in the 30 years. And like Dave Sybeck said yesterday, I think this is my favorite meeting with one exception, and that is the Interagency Space Weather Workshop that we host each year that I will talk about in a few minutes. I've served in various roles at GEM, and they've all been very exciting, and I've enjoyed the experience of working with all the outstanding people in the GEM program. I worked in the initial tail substorm campaign, co-leading some efforts with Dick Wolf, co-leading the metrics and validation focus group. I was an at-large member on the steering committee and now a liaison member. And so GEM has been a wonderful venue and home for much of the work that I've done over the past 30 years. So it's a real pleasure to be here to this well-organized meeting, this virtual GEM. I would rather it would be in person, but glad to be here nevertheless. And I just want to take this opportunity to say a few words about some of the highlights of NOAA activities that have occurred during the past year, especially those related to the GEM program. And for those of you who don't know, our mission is given in the bottom there, safeguarding society with actionable space weather information. And GEM and many of our partnerships with academia and commercial sector and with government, other government agencies, enable us to carry out that mission. So if we go to the next figure, Vanya asked us to include a few words about GEM and the past 30 years. And so I would like to show this figure, which I think Lou Lanzarotti also talked about the other day. And then I showed 2 years ago at GEM, and it says there the goal of GEM is to formulate a mathematical framework that can predict the deterministic properties of geospace. And that goal is very much in line with the mission statement that I just read to you from NOAA Space Weather Prediction Center. If you go on to the next figure, you will see that I want to, again, Vanya asked us to relate some history and thoughts on GEM, and so I have some history and reflection to talk about here. And one is to really relate to you a story that I think probably many of you don't know. It's talked about in the article that's referenced at the bottom by Ernie Hildner, myself, and Terry Onsager. And it tells about GEM's role in the formation of what is now Space Weather Workshop. In 1995, from Space Weather Prediction Center, we began a new link with the space weather research, with the research community. And this new link began to develop when George Sisko and myself and Ron Zwickel coordinated a meeting of the Geospace General Circulation Model Working Group that was held in Boulder. It was, I'm reminded that at this meeting, I gave a talk which would now be considered an operations to research or research to operations presentation. I did this by talking about a fictitious NOAA document, NOAA technical report on how to pick low-hanging fruit, and that is how to move models and data into operations. And I gave examples such as, you know, it should be ripe, but not too ripe, and things like that. Unfortunately, several people actually thought that this was a real technical report. And I got a lot of requests for that, but it contained a lot of guidance that I think is still true today. In 1996, the following year, another GGCM meeting was held, again at what was then Space Environment Center, combined with a meeting called our different version of our Space Weather Workshop. And then the scope changed in 1997 when we brought together not just geospace, but also solar and ionospheric scientists, and what I think was one of the first interdisciplinary workshops in our field. So GEM has played a really important role. If we go forward to the next slide, I want to also have a few other reflections that I want to mention. First of all, GEM's success in part, I think, is from its focus on geospace and bringing together scientists, as has already been said here, in a collaborative forum, but sized to foster interaction and progress. And I think that's the important thing, is that we had a very interactive meeting. And if we look, I suspect we would find that many of the successes and advances in our field either originated in or were enriched through the GEM meeting discussions. And maybe Katarina's data that she showed us 2 days ago can support that notion. A core goal of GEM, of course, was to develop this GGCM. And while much work remains, and in some ways, GEM's accomplished that goal with coupled geospace models, and one of which is in operations at Space Weather Prediction Center. And GEM was an important forum for working with the modeling community and with the metrics and validations group to advance and assess geospace models that are now in operations. And we look forward to more models. Many of the details and improvements many details and model improvements are really needed, as we all know. So as GEM moves forward with a new generation of knowledgeable and creative young scientists, it will be important to prioritize GEM goals so that it continues to be a vital source in understanding and predicting the geospace environment. If we go to the next figure, and here I want to then just begin to highlight some of the activities at NOAA. This figure shows 20 years of data showing our customer growth that we started tracking in this particular way in 1995. In the blue, you can see how that growth has continued over a couple solar cycles now, where the solar cycle waxes and wanes. Nevertheless, the number of customers continues to increase. The next figure, we can see, I want to give a couple of examples here. This figure, the next figure, and the figure after that. Well, before doing that, let me just say one of our major activities at NOAA is that we really need to look at the needs and requirements of the community. And here I've listed 3 publications, which you can find online, the links to, which a couple of them are recent. One was supported by NOAA NESDIS on the economic benefit analysis of space weather products for the electric power grid industry. And on the right, you see another report that's been recently done by the National Academy of Sciences. Now, if we go to the next figure, we'll see an example of one of the models that we are working with. This is a new proposed experimental product. Many of you are familiar with the ovation model, and you can see the probability of the aurora in the color over the polar cap there. But what's been done new by Rodney Varick is to bring in actual observations from NOAA weather satellites, which show the aurora along with that model prediction. So this is very important, not only for many of the people who are interested in aurora and going to see the aurora, but also it has impacts on communications, navigations, and power grids. And so this is a really important product for us and will be in the future. As we go to the next figure, I want to give one more model example that we're working on, and that has to do with the, waiting for the next figure, and the next figure, which shows the operational geospace model, which we are now using to drive a model which produces the geoelectric field. And just in brief here, what you're looking at is about a day's worth of data from a station near Fredericksburg, Virginia, the north-south and east-west components of that field. And you're seeing a comparison between the geoelectric field taken from ground-based, derived from ground-based magnetometers and a ground conductivity model compared to what the model predicts based on what we're seeing in the solar wind. And so that agreement, at least at low frequencies, is very good. And as we expected, it doesn't get all the minute-by-minute variations of the changes in the geoelectric field, but it does incredibly well. So let's go on to the next figure. I want to say something about data here. And this is from El Sayed Talat. Thank you, Vanya. And this is from El Sayed Talat, which shows the vision for the new observations that NOAA needs for space weather. I've often talked about the GOES program, but here it shows observations that could be taken from other vantage points that would support space weather operations and support the science, the data that goes to the science community. In the next figure, I'll say a few words about this year's Space Weather Workshop and next year's Space Weather Workshop. It was an incredible workshop, again, virtual this year. We had over 1,095 participants. If we could go to the next figure, please. It had over 1,095 participants, and amazingly, we had a representation from 47 nations. I looked that up, and that's 25% of all nations. And we gave a lot of attention to diversity, equity, and inclusion. If we go to the next figure, please. It shows that next year we will be holding Space Weather Workshop. It may be in person or it may be hybrid. We'll let you know. And that's going to be April 25th to 29th in 2022. And this just lists some of the major topics that were discussed at our meeting and that I think that you can all relate to with much of your research. If we go into the next figure, we show the pathway from research at the top all the way to operations at the bottom. This is an interagency activity, and I'm pleased to say that in the current budget that was submitted by the department, by the president to Congress, is $5 million to next year hopefully be able to push more models through this process and into the operational environment. And finally, something that is very important to all of us on the next figure, you will see, is the Pro-SWIFT Act, which was passed since the last meeting we had. This act includes it's promoting research and observation of space weather to improve forecasting of Tomorrow Act. It has a lot of things which will help to guide what we do at NOAA, and I think some of the research that is done that feeds what we do at NOAA. And so it includes things like developing formal mechanisms to transfer research into operations, and it supports grants for multidisciplinary science centers that advance our solar and space physics research. So let me end there and take this opportunity to once again just say happy anniversary, GEM, and looking forward to the next years. And I'm happy to take any questions. Thank you.
Thank you, Howard. Really very exciting times for GEM community related so much to space weather and operation to research and so forth. I don't see any questions in the chat or in the Q&A, so let's see if somebody would like to raise their hand and ask a question. Okay, let's see something up here. Okay, Dan Welling is asking, what is the status of the formation of the advisory committee?
Yes, so thank you, Dan. There are several advisory committees with regard to research to operations. One is the Space Weather Advisory Group, which is being formed. Another is the Executive Board of the O2R2O Steering Committee. And another is the National Academy Roundtable, which is being formed by the National Academy. So there's a lot of advisory boards, and I think I expect that we're going to hear soon about the membership, at least of the Space Weather Advisory Group. And I should say that the important thing there is that it includes 15 people, 5 from academia, 5 commercial, and 5 from the user community.
Okay, thanks. So there are no more questions, but we can continue, of course, the discussion in the Slack channels. So let's proceed now with our talk from our new NASA liaison, Jessie Woodroffe. So are we ready with the slides? Yes? Go
Looks
ahead,
good to me.
Jessie.
All right, thank you, Vanya. It's a pleasure to be here today. My name is Jessie Woodroffe. I'm the new NASA liaison to GEM. I'm taking over for my colleague Mona Kessel. This talk isn't heavy on looking back at the history of GEM, but I'll just reminisce that this is my 18th year involved with GEM, and this is long, over the course of my entire career, been my home group. So I'm very pleased to be here with you today, and I do look forward to at least 30 more years of fertile scientific discussion. So this talk is an overview of the last year or so in developments at heliophysics. Could we go on to the next slide, please? I'm happy to say that despite the extreme challenges of the last year, that NASA heliophysics is growing rapidly and in many exciting directions. We are, as a division, poised to achieve the program of record that was outlined in the 2013 Decadal Survey and Midterm Assessment, with the IMAP satellite passing its key decision point C in July. The PUNCH, our polarimeter mission, passed its mission review in July. The GDC has passed a key, has passed a key decision point and is having an instrument solicitation released. We have 5 MIDEX selections that were for step 1 in 2020, and we'll be down selecting those soon. And we have initiated planning for a dynamic mission as well. That would be the last of the missions that we want to complete from the decadal in this 10-year span. We have enhanced and expanded our heliophysics system observatory with a number of new innovative missions, a robust and ever-expanding suborbital program. And we are also exploring, expanding, and utilizing creative rideshare strategies to get even more instruments in orbit. Right now, we've got 12 missions in formulation and another 7 that are being studied. We have the Tracers mission with a Magic Tech demo that's proceeding into formulation. And in December 2020, we announced a mission of opportunity selections for EUVST, which is partnering with JAXA, and the EASY mission. We're investing in a number of different missions and technology explorations to enhance our return on our science. This includes the Solar Cruiser tech demonstration, which is, as I'll discuss a little bit later, a solar sail tech demo, and a new program, or at least thrust in space situational awareness and orbital debris characterization and technology maturation. So We like to say, and we're proud to say it, that NASA currently has its largest and most vibrant heliophysics system observatory in its history. Next slide, please. So schematically, here is the Heliophysics System Observatory. It's 20 operating missions, 27 spacecraft going from near Earth, near to the surface of the sun, to the surface of Mars, and beyond the boundary of the termination shock of the heliosphere. That is an amazing array of locations, instruments, and science opportunities. And I'm happy to say that the science community is doing a great job of making use of all of it. We are developing more missions, more satellites, particularly CubeSats. As you can see, there are a number of them that are in development. Even though there are 3 on orbit, there are 12 plus in development, indicating that we have as mentioned, a robust and growing suborbital and near Earth program. Next slide, please. And just a few highlights here. We had 2 missions of opportunity in the solar terrestrial probes, announced December 3rd of 2020. That's Solar Cruiser, which I mentioned is a tech demo for a solar sail being led out of Marshall. And the GLIDE mission, or Global Lyman Imager of the Dynamic Exosphere, which is being led out of UIUC. In addition, we announced 2 missions of opportunity through the Explorers line on December 29th, and that's the EUVST, which is in partnership with JAXA, but being led out of NRL, and then the EASY mission, which is being led out of Johns Hopkins. There's just a diverse set of science goals being met by these, and too much for me to go into at the moment and cover the rest of my slides. So next slide, please. Some updates on the research and analysis program at HPD. Good news is we are maintaining a healthy and I dare say a robust RNA program. We are maintaining the DRIVE initiative and we're planning for our phase 2 selections. We have established the Early Career Investigator Program, or ECIP, for every 2 years to ensure that most people will get a chance, at least a couple chances to apply. We are greatly enhancing our efforts in engaging and improving diversity in our research. That includes dual anonymous research evaluations, adding new emphases on high-risk, high-impact research, and creating diversity and inclusion-specific solicitations. We are initiating cross-divisional programs, such as with exoplanet research, for which there were 2 selections in 2020, and there's an upcoming solicitation for cross-divisional research related to habitable worlds. There's a strong emphasis in our theory modeling and simulation program for artificial intelligence and machine learning. That was last offered in 2019 and will again be offered in 2022. Of course, any other program involving science and data analysis welcomes the use of AI ML tools. NASA has NASA HPD has a new citizen science strategy where we are trying to leverage participation and involvement of the broader community to increase diversity and education throughout the community. We are doing that in a number of ways, but for example, we are initiated a citizen science seed funding program, which had 4 selections. In 2021, we are planning for a heliophysics big year in 23-24. That year will include 2 solar eclipses during solar max. If you're interested in that or anything related to citizen science, you should contact my colleague Liz McDonald. She's really heading a lot of that up. We've selected 3 new Jack Eddy Fellows. And we continue to have excellent research being generated by the PIs of our programs and indeed all the investigators going into high impact articles in a variety of journals. So good work, everyone. Next slide. There are a number of research opportunities that are either new or modified over the last couple of years. You may be familiar with some of these, you may not. Particularly the suborbital, low-cost access to space missions are opportunities to continue to evolve in order to properly accommodate the opportunities that exist and the technologies that are there for exploitation. As the new missions come online, there are new opportunities to exploit that data and to work with those instruments, hence the gold icon guest investigators, the Hermes interdisciplinary scientists, in ROSA 2021, there will be the GDC interdisciplinary scientists. There are a number of other opportunities coming up, so I encourage you to take a look at the ROSA's solicitations as they come out. As I mentioned earlier, LCAS is very robust with a number of small missions that are in formulation. Next slide, please.
3 minutes warning. 3 minutes warning.
All right, thank you, Vanya. So for those of you who are interested in the statistics of our selections, I will show you here that ROSA 2020, we have made and evaluated almost all of the programs. We are just waiting on H-Fort and GG. The good news is, if you look at the third column, well, under the percent selected column, there's no program here has under 25% selection, and some have in excess of 50% selection. That's showing that we've been getting good support financially for our research programs, and that has led us to be able to select a lot of good research to fund. Next slide, please. After a COVID-related delay through 2020, we've been able to resume our sounding rockets, which is great news for the community. And we have actually had 7 sounding rockets launched since May, 2 at White Sands and 5 through Wallops. The 5 from Wallops are shown here on the slide. So that's Kinetics, Viper, Rock On, and a couple of Dynamo 2s. The White Sands ones are not pictured. Our DoD colleagues do not enjoy cameras. Now, moving on to the next slide. We've had a lot of developments in the space weather program at NASA with the creation of a space weather strategy and implementation plan, the development of a cross-agency framework for transitioning NASA research, technologies, and techniques, the initiation of the NSF-NASA Joint Space Weather Quantification of Uncertainty Grant, the development of an enhanced research operations to research grant solicitation, where we've added an extra year option to allow for the further development of transitionable capabilities to bridge that notorious valley of death. We are moving forward with opportunities related to Hermes and the Gateway. We are taking actions as directed and suggested through ProSwift, as Howard mentioned. We're developing an instrument pipeline to take advantage of future opportunities and make sure we do not miss a chance to put an instrument in orbit when a chance exists. We're engaging heavily with our international partners, such as ESA on their L5 mission, the Canadian Space Agency with their Arctic Observing Mission, the ESA Daedalus, and CASI SNIPE. So, robust engagement with our international partners. And we are actually transitioning the radiation detector instrument on Curiosity rover from planetary science to heliophysics, which gives us on-the-ground radiation measurements on Mars, which makes it multi-planetary, a heliophysics system observatory. Next slide, please. Decadal survey. This was covered by my colleague Jared Leisner, so I encourage you to take a look at his talk from earlier this week. Next slide, please. This is an important topic that unfortunately is not going to get a lot of treatment here, just owing to time, but we are actively working and developing both internally and externally activities that can improve inclusion, diversity, equity, and accessibility in heliophysics, both through our activities and representation in the HPD at headquarters and in our activities that are facilitating the development and support of the community. I really encourage you, if you have any questions about what we are doing or suggestions about things that we can do better, to reach out to me or any of my colleagues at headquarters to engage in conversation about idea. There was a lot of great conversation about this during Helio 2050. I know there are a lot of great ideas out there, and we are working on this, and we are trying to do it right. Next slide, please. So, to summarize, there is a lot of exciting stuff going on. We're putting out a lot of new missions. We're doing a lot of new science. This next year is going to be a lot of important decisions and a lot of great opportunity for the science community. RNA, missions, it's all proceeding, and it's proceeding at a rate that is kind of unmatched in recent history. We're planning our decadal. We're trying to improve as ourselves and for the community. And we are going to keep trying to do well and do better. So, final slide. Please, if you want to contact us, if you want to keep tabs on what's going on, here's information. Please grab the slides after the talk if you want to get these links or these addresses. And as Nikki always says, next slide, please. Remember that Helio rocks. So, thanks everyone.
Thank you, Jesse. Very nice overview and lots of opportunities to get involved. So we do have one question, and I would like to ask Craig Kletzing while we are discussing this to maybe try to share his slides. So the question for you, Jesse, is how does high risk, high impact affect the proposal evaluation?
So high risk, high impact factors into the proposal evaluation by, it is not ranked as a major strength or major weakness as you might be familiar with. And instead, it is a programmatic factor that helps us identify research that may not have been properly considered due to its potentially risky nature. And it is given a second look and potentially given an opportunity for funding through a different mechanism. That being said, we also just want to make sure that everyone understands that identifying your research as high risk or high impact is not a negative. We want you to be honest about the potential risk in your research and the potential impact of your research. And these things are part of your research plan, and it will be considered, recognition of risk is a strength, not a weakness. So.
Okay, and how are we doing with the sharing of the slides from Craig?
Well, it was working earlier, but right now I'm getting a message about who can share.
Okay.
Under advanced sharing options. Maybe let me try again. Let's just try. Oh, here we go. There we are. Can you see that?
Yes, okay. So one last question for Jesse from Hyunju. Do you know when the 2019 H4 results will be announced?
I can say very soon, but I can't give you an exact date on that.
Okay.
I would encourage you, if you have a direct question about that, to contact the program scientist in charge of H4, which I believe is Dan Moses. But I have been told that we are nearing completion on that.
Okay, great, thank you. And we can continue again discussions on Slack. So let's now proceed with the tutorial that will be given by Professor Craig Kletzing. And I would like to ask the students, Lengying and Chi, to introduce him and themselves.
Hello, everyone. My name is Zhang, and I'm the moderator of this plenary session to give an introduction to the speaker. I am a second-year graduate student from the University of Illinois, and now I would let the other moderator, Lengying, introduce herself.
Hello, everyone. I am Lengying. I am a fifth-year PhD student at University of Colorado Boulder. I'll be one of the moderators today giving up the question, I guess, like not introducing, but moderating the Q&A session. So yeah.
It is our honor that today we have Dr. Kletzing from the USA for the plenary talk on MIC. Dr. Kletzing obtained his doctorate from the University of California, San Diego in 1989. And since then, he has been actively involved in research and academic activities. Currently, he is the Donald A. and Marie B. Gurnett Professor at the University of Iowa. His research work includes space as well as laboratory plasma. His research interest includes in situ measurement of the plasma environment in the magnetosphere, in particular, the aurora zone and MIC processes. He also investigates the wave-particle interactions in the Van Allen belt region. He also developed several new techniques for measuring wave-particle corrections using the data from different satellite missions. Now let's welcome Dr. Kletzing.
Well, thank you for having me, folks. The title in the schedule is MI coupling, which is shall we say, a rather broad subject. From things like the auroral zone and alpha waves to, neutral plasma interactions and all the rest. So I'm not going to even begin to attempt to cover all of that. And what I thought I would focus on is MI coupling in the cusp, and particularly tell you a little bit about the mission that we are developing to make those measurements, because once we get this on orbit, I think we'll be able to do lots of things that will directly address MI coupling in this particularly interesting region, which in some sense is a bit understudied, I would actually argue. So this kind of gives you an overview, and let's see if this, I turned on this laser pointer thing. I don't know if it actually helps in PowerPoint or not, but the cusp is this region where when we have magnetic reconnection happen out here on the nose, that particles are admitted into the magnetosphere and they come down the field lines. And so by flying at low altitude, we can look at these particle signatures and use them to investigate some key things about magnetic reconnection that complement that of MMS, which is sort of a detailed microphysics mission. And this is in some sense a complement that lets us look at some of the bigger picture questions. And just to give you an overview, this mission is a pair of satellites will be flying through the cusp at low Earth orbit, about 500 kilometers. And we have them separated by anywhere from 10 to 120 seconds. That's something that we can adjust. And this is one of these key things that people have been talking about for a long time, but we still have relatively few missions where you have things in exactly the same orbit so that you can see something and see if it changes when you go through again just a little while later. And so that we can start to get at some of the details of what are the dynamic changes that are going on, what things are spatial, what things are temporal. A constant problem, in our field is separating those two things out with a single satellite. Let's see. What we do is, so I remember everything I was going to say here. We've done a lot of orbit studies using data from the DMSP to make sure that we will get through that region. And actually about half of our orbits, we get an intersection with the cusp at various angles and things. And of course, that gives us a wide range of solar wind conditions that we'll be able to look at the cusp. It turned out after we did all these studies, we just have to do little tweaks to the satellite to actually get quite a good number of events where what we've chosen to do is sort of taken a page from the sounding rocket program where we orient the whole satellite to be in an orientation that gives us a good coverage of all the pitch angles and in particular things coming down the field line. So here I just quote, what our overall science objective is. And you can see it's definitely aimed at MI coupling and understanding how this coupling between the cusp and the magnetosphere works, and in particular trying to separate out spatial and temporal things so that we can understand which dominates under certain conditions. And this is actually a question that goes all the way back to the early 90s about whether when the signatures that we see, which I'll show you in a moment here, which are step functions, the discontinuities in the ion dispersion features, is that spatial or is that temporal? Some mix of both, some in some cases, some in the other. And that's a question that you simply can't resolve very well with a single satellite. So let me go back to where this kind of all started. And given that this is the 30th anniversary of GEM, I should have to show this slide because way back in the early 90s, I think I went to either one of those first or the second meeting out at UCLA And I remember the entire GEM community fit into one fairly small classroom at UCLA. Shall we say the meeting has gotten a little bigger since then. Terry Anzager was the PI on the grant that we had at that point, and I was working with him. And he wanted to look and see if we could model fairly simply, actually, the signatures that you would see on DMSP. And so up above, you see the data, and down below, you see the model. And it was really a pretty simple model. We just used a dipole field. We admitted a range of different energies. I wrote the code. We mapped this stuff down to low altitude and said, look, we can actually get something that looks pretty close. And in particular, this signature of dispersed ions, which is pretty straightforward in a basic sense of that you have a convection electric field, which causes things to drift to the poleward direction. And so the fast ions basically don't drift as far latitudinally as the slow ions. And so you get the situation where the high ions come in first, the higher energy, and then as you go down to lower energy, as you go further northward. And so this is, sort of a basic kind of thing. And it was, as far as I know, the first real demonstration that if you kind of put those things together in a pretty simple way, that you were getting the right basic story. And so I thought this was kind of fun to show, because this is where the whole idea for this mission that I'm going to tell you a little about came from, was actually this initial work that we did. So just to make sure folks are aware that sometimes things that you're doing now may not come to fruition in terms of a mission for another 20 years, simply because putting all the pieces together and the things that you need to do in order to implement something to resolve a question. There's plenty of opportunity as one goes through one's career to come back and revisit things and make new measurements. So here's the basic goal of what we're going to do. Just a picture. This is from our some of the presentation that we had for how the mission works. And what we have here is, on one side, we're showing a couple of these are, we sort of doctored these up to illustrate what we expect to see on orbit. But what you see here, here's that ion dispersion signature in a lot more detail than you can see with DMSP, where you've got more energy sweeps per second, and so that you or per minute, so that you can actually see all the details. And what you'll notice, these black lines are trying to show you is these little discontinuities, such as right here and right here. That is, these ions come down, they follow the basic kind of form that you expect for the ion dispersion. Higher energies come first, low energies come later as you go northward. But then there are these little jumps. And these, like I say, these questions arose back in the early 90s, remain unresolved to this day, of what's going on with this coupling process between the reconnection site and magnetosphere down to the cusp. And sort of two basic hypotheses were put forward. One is the one that you see here on the left, is that it's spatial. That is, what's happening here is, as your satellite is traversing through the cusp region, basically it's going from flux tube to flux tube, and there can be multiple spots that are actually where reconnection is occurring on the front side. And these map down to different regions in the cusp. And so as you fly through, you're just jumping from one region to another region. And as you might expect, they wouldn't all drift poleward in the same way. And so you see little discontinuities as you go from one to another. A single satellite, that's how it would look. On the other hand, what the other hypothesis, and probably a lot of people favor this one, is that, in fact, what you're seeing is temporal reconnection. That is, it's turning on, and then it's turning off, and then it's turning back on. Again, you would get a discontinuity when that kind of thing happens. And so which one of these two explains things? And so how would you tell the difference? Well, the basic idea is that if it's temporal, then you would expect the entire pattern to continue to drift poleward. Because what you're seeing is something that's happening in time. And so those discontinuities would just continue to drift northward. In this case, we're in the northern cusp. And so you could compare the signature at one time and at a fairly close related time. You don't want to get too far because there could be bigger time changes that happen on larger time scales. And we will look for this pattern to actually drift northward. And we'd say, it's really a temporal process that's dominating. On the other hand, if you fly through and you see basically the same thing in the same position when you go through again later, that tells you that no, in fact, you're probably just jumping from region to region where there's just steady reconnection going on the whole time. And so this is kind of the prime goal of our tracers mission to go after, although we've got other things that have the other parts of MI coupling involved. So another one is to look at this bottom end of the dispersion, and that gives you some information about the reconnection rate. So when the rate goes up, higher convection, things move further northward, so this gets stretched out. When the reconnection rate drops down, lower convection, and you don't move things quite as fast to the northward direction. So we will be passing through this region, once every 90 minutes, roughly speaking, because it's a low Earth orbit. And so we'll be getting steady information about whether the pattern has stretched out or has scrunched up a little bit latitudinally, that gives us a good sense of what's going on a pretty regular basis in terms of the reconnection rate. And I think this will be probably a useful product. And we've already been working with some of the folks at Goddard's for automated algorithms that can look at this bottom edge. There's a sort of a definition that Mike Lockwood came up with many years ago. We have a sort of little seminar series for the team going on, and there's a lot of progress being made. And so I think we'll be able to put this out on a regular basis as something that can help inform space weather. And then we get to kind of probably where my early proclivity is going way back to actually even when I was just finishing up my PhD, and that's the study of alpha waves. And so we know from FAST that alpha waves are observed, but FAST on the cusp, but FAST observed them at much higher latitude. And so we're very interested in looking at this stuff I misspoke, at higher altitudes, but we're very interested in looking at these at lower altitudes, where you can start to tell something about where the interaction would have occurred and what all it was able to do. And so this is, again, we have our cusp signature up there. And one of the questions is whether those jumps that we see are associated with some kind of discrete alphanic activity and electron acceleration. And there is some evidence for that, but since the alphane waves at fast altitudes are sort of in process, you don't get the final signature that you get down at lower altitude. And so we're interested in understanding, are those jumps associated with perhaps small magnetic field discontinuities, which launch the alphane waves and can accelerate electrons? Just the whole process of accelerating electrons, this is from some work I did many, many moons ago, that also show we can look at these dispersive signatures, because when you accelerate alphane waves accelerate electrons. They come zooming down the field line, and it's kind of a similar process to what goes on with the ions, except electrons are vastly faster. And so they come down, and this is a signature that we've modeled back in the early 2000s that showed that you could, the signatures we saw in sounding rockets in the auroral zone did produce this kind of dispersed signature. And we have some evidence that this happens at low altitudes in the cusp, but we will be able to put this together with all the fields measurements that you need to have to get at this coupling process of how alphane waves interact with electrons lower down, where you start to have enough density that you can start to see a fairly significant signature. So this is sort of our third main science objective in the mission. One of the questions that we often get asked is, why now? And the one I usually point out is primarily is that, the community is pretty focused due to MMS on this whole reconnection process. So it seemed like a very timely thing to kind of look at these issues of, is it, happening in multiple places? Is it all temporal? Is it all spatial? How does that get affected by the solar wind? And so with so much of the community focused on reconnection, it seemed like a very, very, it's the right time to go do a mission like this. Plus, the other thing is that the simulation tools are starting to get pretty sophisticated. On our team, Professor Yu Lin down at Auburn University has simulations that she's been working on. She's just extended her hybrid simulation to become global. And so we've been working with her. And so we'll have some good simulation to accompany this as part of the Tracer's mission. And we've already been talking about ways that we can make that data available to the community once we get on orbit with simulation runs, so that people can actually work with this. So we're viewing this almost like as another instrument that produces another data product for the community, because I'm a big fan of getting things out so that various different ideas about how these MI coupling processes work in the cusp can be explored broadly. Because if there's one thing we've learned from the Van Allen probes, is that the more you make the data available to people, there's all kinds of good ideas that people have that we can't think of, or we don't think of, and you get a lot more out of a mission. And so, we have these various, things. This is a little more programmatic in the sense that, we've kept the mission as simple as we can. And really what we've done here is come up with a mission that has fairly standard instruments, but by having the 2 satellite constellation, we can actually do some really, really great science. And we're very flexible. I'll show you a little bit about how we're planning on launching this mission, because it's a little different than kind of the usual thing. And then I'll just mention the TRICE-2 mission. I'll just show you a little bit from that. But that was actually sort of the genesis of this. First, this work way back in the early 90s got me thinking about these questions of dispersion in the cusp and how that MI coupling process works. But then we came along with the TRICE-2 mission, which we launched back in 2018. And as we were starting to develop that, Stephen Fuselier at Southwest Research Institute said, hey, you know, we really ought to propose this thing as a SMEX. And that's where this all started. And here we are today working on implementing mission. We have our PDR in another month. So just to show you the satellite, and it's a pretty, what I would almost call standard set of plasma measurements, but having them in this configuration presents lots of opportunities. And we were focused for the mission on the cusp, but I think these instruments can be used in lots of other ways. So, you know, we have the ion detector here being provided by Southwest Research Institute, and it looks all around the field line. You see the spacecraft are pretty small. I mean, it's always hard to tell the scale, but this is about the size of a washing machine. So these are pretty small spacecraft as it goes. UC Berkeley is providing the booms that our magnetometers go on. So we have a search coil magnetometer as well as a DC flux gate, as well as, which is not shown here, the MAGIC technology demonstration experiment, which will also be mounted. We have electric field booms. And one of the interesting things that we did, took another page from the sounding rocket program to say, well, you know, wire booms are great when you're at much lower densities and you need them to get very far away from the spacecraft. But at these altitudes, the plasma is sufficiently dense that we don't think we're going to have much trouble with. We don't have to have super long booms. And so we will be flying the Berkeley Stacer booms, which we've used on rockets for years and years, which go out but are much more rigid. And actually that makes designing your spacecraft a lot easier because you don't have to worry about all the dynamics and things that go on. We have our main electronics box, quite exciting to look at. We also have our analyzer for cusp electronics, or ACE, and this will be making pretty fast measurements. The ion measurements will be about every 350 milliseconds that will have a full energy sweep, and the electron instrument will make a full energy sweep about every 50 milliseconds. So we'll have really, really good resolution on these things. And we just take data in the cusp and telemeter it down. We're due to telemetry bandwidth. Getting things off, you know, buying the contacts. But I think there are opportunities as we get into extended missions and things like that to actually just target different areas. And since we have this capability of sort of reorienting the spacecraft, we chose that over fancy detectors that can you know, deflect particles. You know, if we decide that later we're going to, let's say, study the auroral zone, we would just camp the spacecraft in such a way as to get good field line measurements in the auroral zone. So I want to talk a little bit about our model and how we did all this stuff in order to make sure that we were going to get through the cusp with our orbit. And what you're seeing here in the sort of yellowish, I'm not quite sure what color I'd call that. That's what the DMSP cusp model would tell you that is where the cusp is. And just as sort of a verification of principle, when we launched these two rockets back in 2018 for the TRICE mission, and when you're doing a sounding rocket launch like that, you know, it was up to me as the principal investigator to say, okay, it looks like it got cusp, go. And after the fact, we went back and compared with where the cusp model said we would see the cusp and where we saw it. And as you can see, the two agreed remarkably well. And we got just a really, really nice data set out of this, which we're still working on today, and papers are starting to come out and things like that. The one disadvantage we sort of had was because these are sounding rockets, which are essentially, you know, how would I say, glorified bottle rockets at a certain level. Once you light the fuse, they kind of go where they go, and you try to aim them as best you can, but they are unguided. And so one of our rockets flew a bit to the right, not so far as to get that big country over there way to the right, as excited as he did back in the early 90s. When jets got scrambled and things like that. If you want to read some history, it's a fascinating thing, but no disasters occurred, but it got people excited. But anyway, we did quite well, but they weren't exactly along the same field lines. And that's one of the things that Tracers is expressly designed to do, is to make sure we're crossing the same field lines very shortly after that, so that we can really get a good comparison. Because one of the things we've run into is the comparison is a little bit on the tricky side. But what you can see here is I just picked out the ion measurements. I could show you measurements from this mission all day, because there's all kinds of great stuff. But here's the measurements from the Southwest Research Institute ion instrument from the two rockets. And you can see here's that dispersive signature. There's some little jumps here. They're a little different. And so we're having a little difficulty comparing these, because we're having to figure out what's the best coordinate system in order to align these things to one another. It turns out something called the dip angle is about the best system we've come up with for doing this at these kinds of altitudes. And that's one of the things when we talk about how are we going to compare simulations with our our data that we've been talking about. If we're going to let people kind of choose what they think is the best system, we'll publish where the simulation results are, because that only comes into about 3 RE, and then we'll let folks do different connections, but we'll make it clear how we've mapped those so that people can do alternative mappings if they think there's something better to use. And I think that's going to be an interesting question in the MI coupling process, is how do you do mappings from things that are a little further out down to low altitude? Because it's not a trivial problem, and particularly in a place like the cusp where it's quite dynamic and the field lines are can be reconfiguring on you. The ways to do that, I think we're going to learn how best to do that by comparing models and the data that we actually see. But just to show that we got some really good successful data, and we're very pleased with this rocket, and it's turning out to be great results, and it got our mission going. And just showing a little bit of the electron data as well, that we got some really nice things. And one of the interesting things is this little feature that you see right here is right where there is a distinct gap and jump in the ion data. And so that sort of supports this hypothesis that we have that there may be alphanic activity in those little pockets that is enhanced. And that's one of the things that we will also figure out in this MI coupling process. And some more data. Here's some of the beautiful waves that we saw in there. And then I always like to point out, and this is actually getting to be a little long in the tooth, because the simulations that you does have moved quite a ways along since this, but it just goes to show that the simulations do show these basic features of ion dispersion and so forth. And so we will be using these for global context and trying to understand what the solar wind effects are on what we're seeing, so that we can put these in a context. Is one of the goals, to my mind, of the Tracer's mission, is to be able to say, if you do your simulation this way, you tend to get more correct answers with what we're seeing on orbit than if you do it a different way. And what parameters do you have to worry about and things like that. So we're trying to close that loop of feeding back into the global simulation world to make sure that we're doing the best job that we can on the MI coupling processes on the day side. One thing that's kind of interesting, and I mean, it's a little bit wonky of me, I guess, but to talk about how we're planning on launching this mission. And we are going to do something called rideshare. And the idea there is that NASA has launched a lot of satellites over the years, but they use a whole rocket for that one satellite. And often that rocket has much more capacity to put mass up into orbit than gets used. And so we've expressly proposed for the idea that we would go in a stack, as you see like this, and then we could fit inside, as you see down here, something called an ESPA ring. And these are often used for CubeSats around the outside, but often that space in the middle doesn't really get used. So we would actually sit inside here, and then you could mount the main spacecraft, the primary mission, up on top. And so you would launch this whole configuration, which could actually have some CubeSats, us in the middle, and another payload sitting up top. And actually, if you look at these things inside the fairings of these rockets, usually all this stuff just sort of sits down here at the bottom. I mean, it's amazing how much space there is when you get in there. But they're worried about like ComSats and things like that to fit. And in this way, we can get more bang for the buck for the launch. And so we're working with NASA to develop the plan for that. We don't have an express launch yet, but we designed ourselves in such a way to be able to tolerate a wide range of things. And the other thing you have to think about in this is you may not get into exactly the orbit that you want, because we want to be in what's called a sun synchronous orbit at about 10:30 in the morning is where we get our best statistics. And we might have to do some orbital maneuvers to drift to that. And this plot just quickly shows this. Like I say, there's a little bit maybe more detail, but things you have to think about if you're thinking about missions downlight is they're kind of two regions, one here at about 2:30 and another one here at about 10:30. This is the orbital plane is defined by those things, of where we get the plot here showing the number of passes that we get through the cusp, or cusp accumulations as we call them. And so, we might in fact launch over here, and then we do some burns, and we gradually drift back over to here in order to get to the spot we want to be. Or we could launch over in here and again do some burns and drift over to here so we can get to our maximum number of cusps where we're getting them about 50% of the time. So let's see, I didn't mean to go into public engagement, so I'll skip over that one. So, this is going to answer some questions, I think, that are long standing in MI coupling. And it really takes this two satellite kind of configuration where they're dedicated to each other with the same measurements. People have tried to do this, in particular, Karl-Heinz Strautner at LASP, to make this stuff line up with different satellites, but it's always tricky. You don't have quite the same instruments. They're not close together enough in time or space. And so the results have been pretty ambiguous about what you actually sort of get. And so by doing this, I think we're going to really get to some interesting things. And I can see also downstream, like I say, extended missions targeting other regions. You could even target, let's say, the equatorial region and look at what's going on there. Because when you have two satellites, you really can start to address the dynamics of the coupling processes that go on. And so these multi-satellite missions, I think, are really just they're going to be great and as satellite sizes and prices come down, we can do a whole lot more. And I think with this strong theory coupling, we're going to do really quite well. So I'll stop there. Hopefully I hit my time mark reasonably well, and can take any questions that you guys might have.
Yeah, thank you, Craig. There are 2 questions in the Q&A right now, and just a reminder to the audience, feel free to use the Q&A options to drop any questions that you have. So the first question is from Eric Lund. He's wondering, are there any plans for coordinated campaign with ground-based assets like RISR or Svalbard, and etc.?
We're still early, but we recognize that. And actually, we have collaborators in Europe, in particular, Tim Yeoman in England, who has actually, I think, with a little help from the tracers is coming, gotten funding to upgrade the Cutlass radars. And also we're working with Jan Moen in Norway to collaborate on ground-based auroral imagers, and plus also ISCAT. We've also talked with, I'm blanking on his name at the moment, Oskavik in Professor Bergen. And so, no, we very much want to do that, because I think when you have these regularly going through the cusp at this altitude, you really have a phenomenal opportunity to compare the in situ measurements with what radars and optical measurements are telling you about the cusp. And, again, working towards this ability to do, sort of remote sensing, if you will, by comparing the in situ with the direct measure, with the measurements from radars and optical instruments. So absolutely on our list of things that we want to do.
All right, thank you. And the second question is from Bill Lacco. He say, thanks, Greg. Will tracers address how reconnection or cusp transients are connected to poleward moving aurora forms? PM? Absolutely.
I mean, my hypothesis is that those jumps that you see and where we see enhanced electron precipitation are in fact where the poleward moving auroral forms are. And we will see if that's borne out by when we get to the data. But again, we certainly plan to coordinate well with the folks in Svalbard, because there's really great optical imaging. We'll be over Svalbard 2 to 3 times every day as we go through. There's always viewing conditions, and anybody who's worked out of with folks up there, sometimes it's just cloudy and you don't get what you want. But no, I think that's another thing that we'll be able to connect, much more directly. What are we seeing that's coming down the field line above where those poleward and moving auroral forms are? What are the electron signatures and so forth that we're actually seeing, and how do those align with these ion features and reconnection? So that's my hypothesis going in, but we will see if it's borne out. As I'm sure Bill could tell you, sometimes you have great ideas that just turn out to be completely wrong. But that's one of the things I really hope that we can get at, in kind of the lower down electrodynamics of the cusp that we can look at, and particularly the connection to alpha waves.
Yeah, there's also a second part to the question. He's also wondering about the connection with the air glow patches and fast flow channels they're observed to traverse the polar cap.
Yeah, again, I think we've got the right set of measurements to do those kind of comparisons. You can have electric fields that have the background magnetic field. You have lower frequency. We only go up to about 1 kilohertz on our search coil, but we'll have some good measurements up there. And then, we've got both the electrons and the ions with, I think, pretty decent resolution for this region. We don't go to high energies. We're not going to be looking at, things that you need to have solid state detectors and things like that for. But I think this is a nice complement of instruments for what we're doing, that we can address a whole variety of things. And like I say, I think downstream, we may target some other areas and do some other interesting work, because even to have this in the auroral zone or the polar cap, we could look at outflow. There's all kinds of things I think that we can do with this set of instruments.
Well, yes, thank you. And another question is from Shin Otani. He said, thanks, Craig. Do you collect data on the night side? And do you have any plan for night side signs?
Right. So right now, as the mission is currently set up, we only collect data in the cusp. And part of that is to keep ops very simple, and we don't do compression on board or anything, which has its pluses and its minuses. The minus is you fill your data recorders and stuff a lot faster. The plus is you don't do things on the spacecraft that you might compromise your data in some way. So we basically just collect the data and send it down. We do that about once a day. What I think there may be some opportunities if funding shows up and things like that. We are not constrained in the sense of operating the instruments. It really has to do with contacts and getting the data down. So I think there may be some opportunities to collect data elsewhere, even while we're in prime mission, if we can get contacts in order to get the data off the spacecraft. Now, the one thing is, since in prime mission, we have to focus on the cusp, we won't get that perfect orientation of the satellite relative to things. And if you were going to, let's say, do solely auroral, you'd can it a little differently just because of how the field lines line up. But nonetheless, you're still getting a lot of really important information. And, I think, we will learn a lot just in the cusp. I mean, one of the things I'm really interested in is when we see these alphanic signatures, are we close enough together that we can actually sort of see, how that signature varies. I also think, like I say, I keep mentioning equatorial, but actually this cusp orientation and just the way the field lines sort of map around the Earth, I think there's some interesting things to do there at 500 kilometers as well. So as I say, for the mission itself right now, no plans to do that, but I think that there will be some opportunities probably once we're on orbit to say, hey, why don't we collect data elsewhere in terms of power and all those kinds of things, operating the instruments. There's no reason we can't. It's just really the cost of the contacts to get the data down to the spacecraft. So that's an ongoing possibility.
Thank you. And another question is from Naritoshi Kitamura. And Toshi is asking, will the cusp measurement be performed in both hemispheres?
As currently set up, no, we were just going to target the northern cusp because it's just, the easiest thing to set up. And I tend to think of that more, but there's nothing to say that we couldn't. And it's just at this point that we can do about one cusp region for each pass so that we can dump the data once a day in terms of our current budgets. SMEC missions are highly constrained, but again, it comes down to really contact time. So there's no reason in terms of the facility of the spacecraft and how it's built that says we couldn't do that. But the other thing comes to this orbital or orientation of the spin axis of the spacecraft. We don't have an ability to keep changing that between north and south because there's a fairly big angular range between those two. We do this slight alignment. It's about 1.25 degrees, 1.25 degrees and a half. Sort of only once per day. So that would be the one disadvantage of going to the southern cusp, is if we're oriented for the northern cusp, then you wouldn't get quite all the field aligned things that you would like to have, but you would still get information. So we had to pick which cusp to go with. And I think that was, in my mind, quite strongly influenced by the assets that we have in the northern hemisphere on the ground so that we can do complementary measurements.
Thank you. And the next question is by Hyunju Connor, and she's asking, the cusp dispersion calculated from hybrid model seems lack of lots of ions in the simulation. And how much does the hybrid modeling improve, and can it create more ions activities?
Yeah, I mean, what I was showing you were very early results, I think from literally almost a decade ago. We had a science meeting last week and you was showing her some of her new stuff. I mean, that model was just a front side. It's now been extended to be a fully 3D larger magnetosphere, so you're getting how the lobe field lines come in and things like that. So I think we will do much better on the simulation results as that evolves. And we're still 3 years out from launching the mission, and so the computational resources and the development of these models just marches ahead steadily. So I think by the time we get there, we're going to have some pretty good simulation results to compare with.
All right, I think we're up for the hours, and we have 2 more questions left. So the next one is by Heidi Nikri. I'm not sure, hopefully I'm not butchering her last name. Heidi is asking, are you planning conjunction with the MMS? And I think that MMS with the string of pearl configuration going through the magnetosheet towards the dayside magnetopause will be very helpful together with Tracer to have resolved the PMAFs.
No question. I mean, we can't, once you're in orbit, you can't really change your orbital parameters too much. So it's really going to be when those kind of conjunctions happen that absolutely. I mean, if we think we're close or even, not super close, but we've got, MMS sitting in the magnetopause where we can, actually sort of see what's going on and how those things are coming in, we will definitely compare. I mean, I didn't bring it up, but on our TRICE rockets, we were quite fortuitous that, the MMS was actually quite near the magnetosheath. And so we're getting some comparisons from there. So like I said, we can't manipulate the orbits to get that because that's very expensive in terms of propellant, which is a very precious resource. But I think just kind of the luck of the draw, the way these things work out, there will be conjunctions between MMS and tracers. And I think those are going to be really, really interesting to look at because now you're getting diagnostics in 2 points and you're getting that fine scale measurement that MMS has that you can compare with what we're seeing. So definitely on our list. We're big fans of collaborating.
Thanks. And finally, by Toshi Kitamura again, and he's wondering, could you tell the length of the electric field booms? It must be related to the measurable minimum length of the structures.
Well, the electric field booms are, I think, much smaller than the structures, which is what you want. You want to measure the in situ field. So I should know the number off the top of my head, but I want to say we're about 6 or 7 meters tip to tip. So we should get good measurements because, structures smaller than that you have, or even of that scale, you have it gets tricky because you get kind of a funny aliasing phenomenon that can happen. But I think for most of the other things, it's a perfectly good scale. And we've had a lot of success with this kind of separation on sounding rockets. One of the things I think will improve here, and again, this is a little bit of instrument detail, is sounding rockets, you just sort of set the bias on your probes and go. We have the ability on tracers to adjust that. So we really optimize the electric field measurement for the kinds of densities that we're seeing on orbit in the cusp. So I think we'll get a pretty good electric field measurement out of all of this. So I think we should do pretty well. I mean, down to scales of, I'd say, a few tens of meters, we should do pretty well.
Great. That is all the questions that I can see. I think that will conclude this session. Thank you, Craig. And I'll hand it over to Vanya now.
And I will stop sharing.
Yes, thank you all for participating and for the lively discussions. Just some quick reminders. We have a focus group concurrent sessions in the afternoon and also a special session organized by our Decadal Future panel about geospace system assets in the evening.
Muted, Vanya.
I'm hearing her.
Okay, I hope you hear me.
Yes, we can hear you.
Okay, so yeah, I was reminding about the geospace system asset session in the evening, and then the queer social event through GatherTown. So I hope to see you all there, and bye for now. Thanks for participating.